hear me up there? Are we good? All right. So last time we left off with NP-completeness. We mentioned that in the Chomsky hierarchy, we're talking about this class here, complexity class of NP, which is non-deterministic polynomial time. It contains the class P, polynomial time, deterministic polynomial time, and the big million-dollar question, literally million-dollar bounty on this question is whether they're the same. And now we're beginning to explore in more detail the class NP and also the class P indirectly. So that's sort of where we are in the roadmap. Yes. Oh, it's working now. So we're good for now. Yeah. All right. I appreciate your coming. All right. So as far as NP-completeness, it's a study of tractability, what can be done in non-deterministic polynomial time, and it's a study of parallelism, a study of bundling together large classes of problems and treating them as like entire groups simultaneously proving things or disproving things about them rather than treating them individually. And that saves, it's a big point of leverage. It saves a lot of time and effort because together they stand, together they fall with respect to intractability, and that's a good thing. So we analyze entire classes of problems rather than individual problems, and that's the whole point behind completeness theory, in this case NP-completeness. But all the other classes have completeness theories associated with them. Right? There's problems which are P-complete, exponential time complete, polynomial space complete, and so on. Okay, so the main diagram here was this. We've seen this before. Right? It's a reducibility of a problem A to a problem B, or a language A to a language B equivalently. And basically, this mapping F between these two languages preserves membership, set membership. So W is in A if and only if F of W is in B, and it's an if and only if. So if you can solve problems in A, you can solve problems in B, or vice versa, depending which direction the reduction goes. Now here, we put a restriction that this mapping has to be polynomial time itself. So this mapping has to be efficient. You can't just take your sweet time about mapping, take arbitrarily long to do it. It's got to be in polynomial time. Okay, so now we watch our resource consumption as we map problems from sets to other sets. And that makes a huge difference. So we said if there's a reduction from A to B, and you can solve a problem B in polynomial time, then you can solve it in polynomial time for A as well, because to do that, all you got to do is hit it with a reduction, solve it in B, and you're solving it for A, the set membership problem. Okay, and that's a very important touchstone kind of diagram and notion and concept. Any questions about that? I mean, it's so important that I'm repeating it probably for the third or fourth time, but it's worth it because it's so important and so fundamental to everything we're doing, have been doing, and will be doing for the next few weeks. So it's about problem transformations. For example, we can transform satisfiability to colorability, and we'll show you exactly how such a transformation will work. It's not trivial. Those are subtle. Some of them are complicated transformations. But satisfiability is a problem of given a Boolean formula, whether it's satisfiable or not, whether there's a way to tweak all the variables to true and false in such a way that makes the problem true. So the basic definition of NP-completeness, the problem is NP-hard if every problem in NP reduces to it in polynomial time, in the sense that we just showed, this reduction. And it's NP-complete if it's NP-hard and one more thing, and that one more thing is it itself must also be in NP. The first condition, number one, the problem could be NP-hard if everything in NP reduces to it, but it itself may or may not be in NP. It could still be NP-hard in that case. But it's NP-complete if it's NP-hard, and on top of that, it itself is an NP. So the vicinity of NP looks like this. There's P, polynomial time, deterministic polynomial time that we know and love. Outside of that is NP containing it, but not known to be a proper containment. Right? And here's co-NP, the complements of all the problems in NP. We already know that P and co-P are the same, so that one is not an open problem. Right? So I don't have to write some region here that'll be co-P because we know it to be the same as P. That's a theorem, and it's very easy to prove, right? Take the problem, solve it in polynomial time, and if you want to solve the complement of that problem, solve the problem and flip that bit. Right? That's all you got to do. So whenever there's a solution for a problem in P, there's a solution for a problem in co-P that's just as efficient as the first. They're both polynomial time. So it's an if and only if, so P and co-P are the same. Okay. And we mentioned satisfiability. Given a Boolean formula, is it satisfiable? So here's an example of a satisfiable formula. Here's an example of a not satisfiable formula. And the satisfiability problem is basically to determine which is which. I give you a Boolean formula, and you tell me if it's satisfiable or not. You don't have to give me the assignment of the variables that satisfy, notice, just whether it's satisfiable or not. So Cook's theorem basically maps every non-deterministic polynomial time computation to a Boolean formula that's satisfiable if and only if that computation accepts. Okay? And the way it does it, it takes an arbitrary Turing machine computation and models using lots and lots and lots of Boolean variables all the steps of the computation. At step I, which state the machine is in. At step I, which cell tape position the read-write head is pointing to, right? At step I, which content of each cell tape is, which symbol from the alphabet is residing in that tape cell right now at step I, and so on and so on. That's a lot of variables. They're parameterized by these indices denoting the number of steps I, and in this case, the state of the machine, or the finite control of the machine here, Q sub k. So k is the parameter for the state of the finite control, the finite automata portion of that Turing machine, right? The read-write head positions are parameterized by h's. H sub ik is true if and only if at step I, the machine's read-write head scans the kth tape position. And S sub ijk, that's parameterized by 3 indices. At step I, the machine's tape cell J contains the alphabet symbol S sub k, or sigma sub k, whatever that symbol might be. So that's a bunch of variables denoting the complete state of the machine at the moment. So based on which variables here are true or false, you know exactly what the machine is doing at that moment. It's an instantaneous Kodak moment where you take a snapshot of that machine in the middle of the execution. But it's not enough to just have the variables having the state of the machine. You have to denote now with clauses which state transitions are allowed to happen and which are not allowed to happen. Okay, so you have to say at each time I, the machine is in exactly one state and not in 17 different states. The read-write head scans exactly one tape position and not 12 of them. Right? All cells contain exactly one symbol and not 1,000 symbols at once. And at time 0, the machine is in its initial state. At time p of n, that polynomial that it runs under, because it's a polynomial-time machine. At time p of n, it's in the final state, or a final state. It could be more than one. And very importantly, you have to encode the transitions also as clauses in this giant Boolean formula that we're constructing. Right? And the transitions basically encode all the valid ways to transfer from states to other states. So what you get is a giant Boolean formula that's true if and only if the original machine stops and accepts its input. So what have we done here? We've taken an arbitrary machine, an arbitrary input. You see how much mileage we're getting out of this prop here. It's all the same idea over and over again, these mappings. Take an arbitrary machine, arbitrary input. That machine runs in polynomial time, but it's non-deterministic. You take this machine and you encode it and you transform it into a new machine. And that machine really is a Boolean formula that encapsulates, models the complete behavior of this original machine input pair. And this Boolean formula is a satisfiability instance. That Boolean formula is satisfiable if and only if the machine holds on the input. For an arbitrary machine, arbitrary input, given the machine runs in polynomial time on that input. So it's exactly the same kind of transformation that we did before, except it's more subtle. First of all, the transformation had to happen in polynomial time. And notice there's a polynomial number of clauses in this giant formula that we're building up. So the polynomial time transformation was an efficient one because it was polynomial time. It wasn't just an arbitrary transformation. And number 2, we transformed this machine and input pair into a Boolean formula this time, not another machine. Okay? So that red M prime is a bit of a misnomer. It stands for a Boolean formula this time, not another machine. But the point is, if there was an oracle, a black box, a subroutine that tells us if a formula was satisfiable or not, that will immediately tell us whether that machine will hold on its input and accept it or not. So if we can determine satisfiability efficiently, we're determining the outcome of arbitrary non-deterministic computations efficiently. And that arbitrary non-deterministic computation was an arbitrary computation in NP. We didn't pick and choose. We didn't pick favorites. Take an arbitrary computation in NP, and you can transform it into this Boolean formula in this way, in such a way that the formula will be satisfiable if and only if that computation accepts. So with this theorem, you've done a specific instance of this right here. Every problem in NP was transformed into this specific problem, satisfiability, and that transformation was efficient. It was in polynomial time. How many see what's going on here? Okay, it's not enough. I see maybe a third of the class acknowledging it. Ask me questions. Yeah.
Why can't this be used to solve the halting problem?
Why can't this be used to solve the halting problem? Because if you use it to solve the halting problem, or I should say if you try to use it to solve the halting problem, it's because it's not going to work, you cannot bound the size of this satisfiability instance. This transformation will not be polynomial time. In fact, it won't be bounded by anything, because that computation can go on for a long, long time. It can go on for arbitrary amounts of time. In fact, some of them will not halt. So that formula will keep growing and growing and growing, and you'll never get a finite formula that you can submit to an oracle that determines satisfiability. So let me answer that a slightly more specific way. The number of Boolean variables involved here is polynomial. Why? Because we say at step I, the machine is in state K. Well, the machine runs in polynomial time. There's some polynomial, P sub n, P of n, that's like quadratic or cubic or fifth degree, that the machine will always halt within, say, quadratic time. And so the number of steps here, I, will be between 1 and quadratic, or whatever that P of n is. So there's, I goes from 1 to n squared, let's say. If it's n cubed, then fine, but it's finite, it's polynomial, in fact. The number of states of the machine here is not just finite, it's a constant finite number. It's not just polynomial, it's a constant, it's a fixed number. It's a specific machine that has 17 states or 35 states or Googleplex states, but it's just finite. So it's fixed throughout this whole thing. So K is a constant. I goes from 1 to that polynomial, say n squared. So there's only a polynomial number of Q's and a polynomial number of H's. In fact, it's quadratic or quadratic if P of n is quadratic. This one, ijk, I goes from 1 to quadratic. Right? The tape cells will go also from 1 to quadratic because you can't use more tape cells than you have time to use. So the space will never exceed the time. How many get that at least? Okay, good. That's a lot of you. And the symbols in the alphabet is a finite set of symbols. The alphabet is a finite set of symbols, so that is just some constant. K goes from 1 to a constant. So this goes from 1 to P, this goes from 1 to P, that polynomial, whether it's quadratic or whatever. So the number of S variables is at most the square of this polynomial. How many see that? Okay, because it's indexed by two things that go up to that polynomial, so it's the cross product of all combinations of that number, and they're both that polynomial P right here, the runtime of the machine. And then, so there's many S's, there's quadratic in P. But nice thing about polynomials is that when you multiply them together, you get another polynomial. Another nice thing about polynomials, even more importantly, that you compose them, you get another polynomial. It doesn't blow up, exponentially on you or worse. So if P is a polynomial, then Q is a polynomial. P of Q of n is a polynomial too. Okay. How many get that part? Polynomials composed to yield more polynomials. Good. So P is a very robust class. We'll talk about that separately. Yeah, question?
So the number of possible configurations is finite?
The number of possible configuration is a function of that runtime. But it's polynomial in that runtime, not exponential.
So what's the premise for nailing down the specific cases, the configuration of the machine where it would terminate, where it would have an
The machine always terminates. So this is not an arbitrary Turing machine. It's a machine that runs in polynomial time. Polynomial time. So it always, not only does it always halt, not only does it not run forever, i.e., not only does it always halt, it halts within polynomial time. So it's a double whammy on restricting what it's doing. So it cannot run forever, and it can't even stop in exponential time because that's illegal too. everything in NP runs in polynomial time, right? So this class NP right here is a very small restricted class of the class of all computations. Let's look at the bigger picture again because it's really worth it. Right, so looking at the bigger picture, there's NP. Yes, it's decidable, but decidable can run in arbitrarily large times, not infinite times, but arbitrarily large times. Exponential time, double exponential time, factorial time, really worse, really bad, inefficient, space consumption and time consumption. But this one here, both P and NP run in polynomial time. So every computation here halts. There's no halting problem in here. There's halting problem out there. There's the halting problem H. It's in this class here, but not in this class. Same, let's say the regular languages. Why isn't there a halting problem for finite automata? Why don't we worry about halting when we run a finite automata? Why is it undecidable to determine whether a finite automata halts? They always halt. Finite automatas process one character of input per state transition, and when they run out of input, they either accept or reject, but they halt in either case. Okay. Context-free languages, right here. Why don't we worry about the halting problem for push-down automata? Because the halting problem is also solvable for that. They always halt, or else, if they don't halt, because I can empty and fill the stack and empty and fill the stack and technically run forever. But if they do, we can detect that. Why? Because they will repeat a state. And if they repeat a state, a stack, some state combination, we can algorithmically detect that by keeping track of all the state that the PDA has ever been in and see if it repeats a state. If it does, it will keep repeating that state, and then we can stop and say we'll run forever. So we're solving the halting problem yet again. So when the machine model is primitive enough, like finite automata, and even push-down automata, halting problem doesn't rear its ugly head. But the languages you can recognize using these more primitive, more restricted computation models, those languages, those problems are simpler than the general problems that Turing machines can solve. So the more you can do, the more power you have, but the more issues you can have too, like undecidability and the halting problem not having an algorithmic solution and so on and so on. So with great power comes great responsibility, right? Who said that? With great power comes great responsibility. Famous line. Yeah, Uncle Ben. It wasn't Peter Parker, it was Uncle Ben actually. But anyway, so yeah, when you have more computation power, yeah, you can do more, but more issues fall in your lap, and you have more to worry about, like undecidability and the halting problem and lots of other issues. How much space and time you might be using, it's hard to determine it, and so on. Okay, so I hope I answered that question. Go. Okay, good. So satisfiability seems to be as hard a problem as any in NP, which is kind of amazing because it looks very innocent, satisfiability. I give you a Boolean formula, you tell me yes, no, is it satisfiable or not. Worst case, how do you solve it brute force? If I give you a formula and say, you're going to get $1 billion if you can solve it within the next 24 hours, tell me it's satisfiable or not. So you write a piece of code to do that. What will your piece of code look like? And don't tell me you're going to miss out on it becoming a billionaire overnight. How will you do it? Yeah, go through every combination. Just build a giant truth table with every, and see each one, whether it satisfies or not. And yeah, in 24 hours, you can go to trillions of combinations. So hopefully the formula will not be too large. Maybe 30 variables, 40 variables, you can do it in 24 hours on a computer. But if I give you 1 million variables, that ain't going to happen in 24 hours. Because 2 to the million is bigger than the number of particles in the universe. It's bigger than a Googleplex, or bigger than Google at least. Probably not as big as a Googleplex. So if the formula gets large enough, that method would fail in terms of efficiency. It will still be correct in terms of absolute truth and correctness. Same method, just trial possibilities. But for satisfiability, the best algorithm we know, after all these decades of trying to solve it efficiently, is that one. try all possibilities. We know of no better method than that. Of course, we can take a few shortcuts, and if one of the terms is just a zero, then of course it's not going to be satisfiable. So you don't have to try all combinations. One of the terms is just a plain zero or false, and you ain't going to end with the truth with any other terms, no matter what they are. So you can take a few shortcuts like that. But other than these obvious trivial shortcuts that don't happen very often, generally we know of no better algorithm than brute force, try all possibilities. Same for traveling salesmen. Same for binning problems, for scheduling problems, for Steiner tree problems, right, for packing problems. We'll talk about all those separately. And why do we not know about efficient algorithms for all of them? Several reasons. But the last reason will be the best reason. Several reasons. One is they're all kind of hard and tricky and involve a lot of search in an obvious algorithm, and it's not clear how to do it in a non-obvious way that avoids brute force search. Another reason why they're so hard, people have been working on them for decades and decades, and they didn't succeed in solving any of them efficiently, so you kind of say, okay, they must all be hard. But the best reason why they're all so difficult is that they're all NP-complete. And now we know that. And that means that if you can solve one of them efficiently, you can solve everything in NP efficiently, automatically, instantly, as a corollary to solving just one of them efficiently. How? By these reductions, by these transformations. That one there. How many are seeing more of what's going on now than before? Okay. I'm not sure if we picked up some people or lost some people with all that explanation, but we'll keep going and hopefully it'll be clear. Okay. So the problem of satisfiability is hard because you can construct a polynomial-time number of variables and then conjoin them into clauses in a way that keep them depicting the correct state of this machine as it executes, and so that Boolean formula will be satisfiable if and only if that machine will halt at its input. So you're solving the restricted halting problem for machines that run in polynomial time that don't have a hard halting problem to begin with. But you're trying to solve the halting problem a little bit more efficiently than just running it in polynomial time. Remember, it's non-deterministic. So running it will be more than polynomial time if you have to keep track deterministically of all the threads. The height of the computation tree will be polynomial, that p there. This p here. But the width of this computation tree will be exponential in p, so it's not polynomial. It'll be like 2 to the p, or 3 to the p, whatever the branching factor is of the non-determinism in this machine. So that's what satisfiability is. And we mentioned that it was discovered, this theorem, that satisfiability is NP-complete, that it's as hard as any problem in NP, was discovered by the American Stephen Cook and the Russian Leonid Levin at the height of the Cold War in around 1970-71, and they didn't know about each other. And for 10 years, the world didn't know that they came up with the same result independently. There was no internet, there was no web. Scientists were restricted from traveling to other countries in those days from the Soviet Union or to the Soviet Union. So, yeah, it's too bad they didn't meet early on and had the chance to talk about it. Would have been a great collaboration, sorry. Freudian slip. Freudian slip is when you say one thing and mean your mother. Yes, question up there. Excellent. I was waiting for somebody to notice that. So this proof shows that it's NP-hard, that everything in NP reduces to it. But what we didn't show is the second condition here, that it itself is an NP. So we showed that it's NP-hard. Usually the second one is easy to do. It's much easier than the first. But let's cross that T now. Let's show that it itself is an NP, that there's a non-deterministic polynomial time algorithm that solves satisfiability in polynomial time. Anybody want to take a crack at that? Yeah.
We did this last time. You all, for each variable, choose one or the other and non-deterministically go through so that at the bottom you've chosen every possible combination and then just solve it.
Yeah. So at the bottom, what do you do at the bottom when you get to the bottom after this series of guesses, yeses and nos?
You collapse it. You test that.
Yeah. You have to test. So what he's saying is, here's a non-deterministic algorithm that solves satisfiability in non-deterministic polynomial time. Pick the first variable, go left or right whether you think it's true or not, and then pick the second variable at the second stage of the second level of the tree, this non-deterministic computation tree. Go left and right on the second variable. Now you got 4 different options or states that you're in non-deterministically. And then pick the third variable, guess the assignment for that. So you can think about it as guessing, right? You can go left and right, and you can think about it as guessing whether it's yes or no. And by guessing, I don't mean like picking one and running with it, but pick both non-deterministically and cover all grounds. But after you go through n guesses, basically you've exhausted all possibilities of yeses and no for the n variables. And at the bottom, one of them better accept for the whole tree to accept. That is, you have to check now whether it's satisfiable or not, given the sequence of guesses that got you there to the bottom of the tree, going left and right until you hit the lowest level of the tree. Now you have to check or verify that the answer is actually correct. So you have to plug in all these values into the formula, collapse it to true or false, and see it better be true, and then you say yes, if and only if it collapses to a true or evaluates to a true. If it evaluates for a false, don't say anything or say no. One of the other branches will be the correct one if there exists a branch altogether that gets you to a yes confirmation or verification. So the whole thing is a non-deterministic algorithm running in polynomial time. And how big is this polynomial time bound as a function of the number of variables, just to see if you understand the big picture here? How much time have we expended, non-deterministic time, but time nevertheless? What's the time bound of this? Linear time. I mean, you see linear time going on here. There's only a few people raising their hands, so I'm not sure if most of you are following this. If you're not following this, believe me, there's no point going forward, because it's just going to get deeper and more complicated. So let's get this nailed down tighter here. This is the easy stuff. Ask me questions. How many are reading about this in the book? Okay, that probably explains why I see so few hands. Only a few people raise their hands saying they're reading. I'm just curious, why aren't you reading about this in the book? I mean, this is deep stuff. I've already told you that. So if you just think for an hour of lecture, you're going to, get it all nailed down in your head. You're very, very wrong about that. You need to read about it in the book, look it up on the wiki, look at other lectures about NP-completeness, at least at the high level. So I can only do so much in 2 lectures a week, right? I mean, I'm recording these lectures, but still, it's not enough. You should read the book. You should look at other sources. Look at other ways of explaining it, right? This is not easy stuff. I know it. I admit it. I'm telling this to you. But you need to do the heavy lifting. I mean, I'm your coach, but you're the athletes, right? I cannot do push-ups and sit-ups for you. I mean, I could. It wouldn't do you any good. You need to do this stuff. So I'm telling you how many sit-ups and push-ups and miles you got to run. But you got to do that. I mean, otherwise, this will be very obscure and obtuse and mysterious. And that's not great for you. Ask me more questions. Yeah.
So we proved that there is a non-deterministic polynomial time algorithm to solve the problem.
Yes. We proved that there's a non-deterministic polynomial time algorithm to solve the problem. In fact, it ran in linear time.
Yes. But would we also have to prove that it's NP, that is in NP, that there is no deterministic polynomial time algorithm?
No, not that there's no deterministic polynomial time algorithm, just that there is a non-deterministic polynomial time algorithm. We don't know if there is a deterministic one or not. That's the P is equal to NP question. If there was a deterministic polynomial time algorithm for this, P will be equal to NP and you'd get your $1 million.
That makes sense. So we only have to prove that it's like in the superset of NP, but not in the
Yes.
that it's not in the subset.
Yeah, so we don't know if it's in P or not. All you got to show is it's in NP. Okay. Now, NP contains P. So if it's NP, it may or may not be in P. But whether satisfiability is in P, that's a wide open question. It's been open for 45 years, since 1970. Actually, since before, because we didn't even know it before 1970. So showing that a problem in NP is usually the easy part. Why? Just give a non-deterministic algorithm like he did, guess an answer, and then verify that the answer is true. So guess and verify is usually the typical, archetypical, non-deterministic algorithm to solve a difficult problem in NP, or any problem in NP actually. First you guess the answer, and then you verify that that guess was correct. The verification step is usually easy. If I give you a bunch of zeros and ones and say, does that satisfy? We'll just plug them in and collapse it to either yes or no, and you'll know. It's easy to do, linear time usually. But if I say which combination of zeros and ones will do this job, that's when the problems begin. I mean, it's easy to do with brute force, but there's exponential number of possibilities. So how would you do it efficiently? $1 million question. But what we're proving here with the NP-completeness theory is that all of NP reduces to this problem in polynomial time, which means if you can solve this problem efficiently, deterministically in polynomial time, all of NP, same thing. You can solve all of NP deterministically in polynomial time using the same algorithm for SAT. First reduce it to SAT, then solve SAT, then you'll know the answer over there. Right? That's this business here with the props. Right? So if you want to solve a problem that you're not sure how to do efficiently, reduce it to SAT. Give it to a SAT oracle. He will tell you, and that'll be the same answer to that, given that the reduction works. And this reduction of everything in NP to SAT is called Cook's theorem, and that's what we just went through. That's this thing here. Yeah?
When would it be useful to some of these NP hard without necessarily?
When it will be useful is asking to know that it's NP hard and not NP complete. It'll be useful to know on the way to proving that it's NP complete. Because then you proved half of what you prove one of the two conditions that are necessary. You prove this one, and now all you have to do is prove this one. This is usually the easy one. So even though there's two things you need to prove, if you prove this one, you're 95 or even 99% of the way there. Because this part is usually the easy part. Just guess and verify type algorithm usually does the job. There's a few cases where it's actually difficult to prove the second part as well. That a guess and verify will not obviously solve that problem. You have to be much more elaborate than that. But so when it will be useful, on the way to show that something is NP-complete, or let's say you can show it's NP-complete, you can just show it's NP-hard, that's already progress. Because that means it's at least as hard as everything in NP, and may not be as easy as anything in NP. In other words, it should be worse than NP. And there's plenty of problems that are much worse than NP, like exponential space complete, or double exponential time complete. Right? And those will also be NP hard, but they're not NP complete, because they're not even in NP. They're way above. But they're still NP hard. You can reduce all of NP to one of those two. But that itself was not in NP. So if you show it's NP hard, you're showing it's at least as hard as NP. If you're showing it's NP complete, you're showing it's at least as hard as NP, but not more than NP in terms of difficulty. So I hope that helps clarify the situation. But they're both very useful. If you show it's NP hard, that's already a stamp on this problem saying it's very difficult. You should not try to solve it exactly, but go for heuristics. So if you're working at Google and they give you some problem to work on, with a search engine problem or some database problem or file system problem or advertisement auction problem, these are all typically NP-complete problems rotating around these common tests. And you're not sure how hard it is, and you start working on it, trying to code, and you don't succeed coming up with an efficient algorithm. But as an aside, if you can show it's NP-hard, all bets are off, and that problem is at least as hard as NP, and chances are not only you can't solve it efficiently, but none of the other Turing Award winners that came before you could solve it efficiently. Nobody's collected that $1 million from the Clay Institute yet, bounty on this problem. And so chances are you can now step back. Not chances are, you should now step back and say, okay, I'm going to try to solve it heuristically with an approximation algorithm, kind of good enough kind of answer, but not necessarily exactly in terms of an exact solution, because that's kind of hopeless. So you treat it like you treat traveling salesman problem, or Steiner tree problem, or binning, or packing, or anything that's NP-complete. Because NP-hard is at least as hard as NP-complete, and possibly harder even. Question?
You mentioned that algorithm is not deterministic testing, and that runs in linear time. Is there really a meaningful class for non-linear or non-deterministic linear time, or just deterministic linear time?
Both. You can say that Deterministic linear time is a complexity class. It's also a property. Non-deterministic linear time is also a complexity class. Whether they're the same or not, open question. Also, you can talk about quadratic non-deterministic time, cubic non-deterministic time. Whether they're the same as each other, not open question. They're definitely containing each other properly. Why? Why does, let's say polynomial time, let's leave non-determinism alone for now. Why does quadratic polynomial time properly contains linear polynomial time? I don't even need to say polynomial at this point. If I say quadratic time, it is a polynomial, so I'm being redundant, superfluous, and unnecessarily repetitious. There I went again. Joke. You can laugh. Okay, but what allows me to say that quadratic time properly contains linear time as a complexity class? Yeah, what do you say? Yeah. Everything that runs in linear time runs in quadratic time, so linear time is contained in quadratic time, but what makes them not equal? Maybe they're the same. And it's still contained in one another, but what makes them not equal? The density theorem. Yeah, the time and space hierarchy density theorems. Whenever you have density, the density theorems for space and time, for space it's very, very dense. If you have a asymptotically tiny amount of extra space, you have new problems that you didn't have before, so it's proper containment. For time, we said there was a logarithmic jump. If you're more than a log factor in terms of time, you gain more languages, infinite number of more new languages that you couldn't do in the lower time bound. So the time and space density theorems imply immediately that linear time is properly contained, not just contained, but properly contained. It's not equal to quadratic time or cubic time or quartic time or quintic time or any higher time than that. And certainly exponential time super contains properly all these polynomial classes and so on. So, but right now we're not splitting that hair of how high the exponent is in these polynomials. Right now we're just saying any polynomial. We're being very, generous and unassuming. We're not looking for a really good, great polynomial. We're just looking for any old polynomial as opposed to an exponential. Remember, up to this point in the class, we didn't split hair about time and space whatsoever. We just talked about what's possible in any amount of time or any amount of space. And some things were not possible, no matter how much time or space you chose to expend. Like what? Say it loud, say it proud. The halting problem. That's not solvable no matter what. You want to throw, exponential, factorial number of times the factorial, apply nested, you want to throw that much time or space at a problem? Halting problem, that's not enough. No amount of time or space will be enough because there's no algorithm for them whatsoever. That was pretty bad. And now that we had all this infrastructure under our belts, intellectually speaking, now we can start splitting hairs about what we can do in polynomial time and what we can't do in polynomial time. If we had more time, this was a longer class, we can start splitting hairs about the size of the polynomials, whether it's linear, quadratic, n log n, n cubed. But that's even harder. It's called analysis of algorithms, basically. That's a whole separate kind of study and class, and kind of trying to nail down a time and space complexity even more precisely than we are now. But that's for specific algorithms, like sorting and searching and matrix multiplication. Here we're talking about the entire class of algorithms that can be done in polynomial time. So we're talking about very large classes here. So the bounds will be a little looser, because it's hard to make very definitive statements about infinite classes of algorithms. And it's hard to make definite statements about a single algorithm like merge sort. The fact that merge sort runs in n log n time is not easy to see right away, right? Until you write the recurrence relation, solve it, and whatever. And some algorithms, it's very hard to determine how fast they run, even though they run efficiently. Okay. Yeah, that's a very insightful question. He's saying, what proof techniques do we think will work here? Let me answer the question from the other direction. We have some really good idea about what proof techniques will not work to resolve it one way or the other. And that's probably dovetailing and diagonalization. They probably will not work here. And the reason I say that is because, so in the late 70s, after this was open for like a decade, some very clever mathematicians you're a computer scientist, so obviously you can't solve deep theorems like this. But we are here professional mathematicians. So step aside, children. We'll solve it for you. That's sort of what math did or tried to do to computer science. Now, to their credit, these mathematicians were very clever. So they hit this problem really hard. They couldn't solve it, but they did solve something else. They showed the following kind of amazing result. Now, remember what we talked about oracle computation relative to an oracle. If you have an oracle to solve one problem, all of a sudden another problem can be simplified, right? So for example, if you have an oracle that determines the minimum element in a set in constant time, you could all of a sudden sort in linear time. How many can see that? How? Find the minimum, write it down, delete it, find the minimum of the or change it to infinity, right? In the big array, unsorted array. Find the minimum again, write it down, change that to infinity. Find it. So if you had an oracle for minimum, you can solve sorting faster than we know it can be solved, because n log n is a lower bound for sorting under the decision tree model. Okay, the point is if you have an oracle, other things can simplify. So if you have an oracle for the halting problem, you can solve the halting problem. How? Ask the oracle. Okay. Having said that, they showed that there exists an oracle for which p is equal to np. Separately, they show that there exists another oracle for which p is not equal to np. Separately, they show that there's an oracle for which p is not equal to np, but np is equal to co-np, another open problem. And separately, they showed an oracle for some other combination, and so on and so on. Those oracles were really hard to find, and they're very tricky, and they're hard to describe even, never mind finding them. If I try to explain to you what these oracles are, just trust me, it's not going to be a good use of your time. You can look it up for extra credit if you want. Okay. But here's the point. All the known techniques of proving equality or non-equality of complexity classes survive oracle attachments. In other words, if you attach an oracle, the proof remains the same and you get a similar result like you did before. Remember, the halting problem, we said that there's problems that are more undecidable than the halting problem. If you had an oracle for the halting problem, this other problem remains undecidable, even if you had an oracle for solving the already undecidable halting problem. For example, the halting problem for Turing machines with an oracle for the normal undecidable halting problem, the oracle problem for Turing machines like that is doubly undecidable, even with such an oracle. So, and the proof was very much the same. That proof survived the attachment of the oracle and went through pretty much identically. Anyway, the point is that we're not sure what techniques can be used, but we have some very good ideas about which techniques cannot be used, and that's pretty much most of the known techniques. So to solve this problem, not only you'll have to come up with really, really clever ideas, you'll have to come up with whole new proof techniques altogether. Examples of which are diagonalization, dovetailing, simulation. Those are not likely to help you. And by the way, this problem could be independent of the axioms. We don't know that it isn't either, like the continuum hypothesis or the parallel postulate of Euclid. How many remember that independence of the axiom discussions we had earlier in the semester? A dozen of you? Okay, I'll take it. Now, this is esoteric stuff. What else? Yeah.
Is it possible that this is like a question that falls under Gödel's?
Yeah, that's what I mean by, so it could be independent of the axiom, or it could be one of those Gödel incompleteness theorem situations where it's true but not provable, that there is no proof for it. That could happen too. We don't know that either, whether that's the case or not. So one way to explain why it was so hard to find a proof for this in the last 45 years, maybe there is no proof. Maybe it's just true or false, but there is no proof either way. Is there a way to prove that? I don't think so. But it gets pretty esoteric. Well, let's put it that way. You can't prove it in this normal logic, or, first order, second order logic, but in some higher logic you may be able to. But it's no longer the logic that we know and love and use every day, arithmetic and algebra and so on. Let's just leave that one at that. Okay, any other questions, maybe more mundane questions You know, because a lot of you said you don't even get this, you know, Cook-Levin theorem. So here we are talking about much more esoteric things. You know, I don't want to open too big of a can of worms on you if you don't even see the first worm. So mixing my metaphors. What else? So we have satisfiability. It's difficult as anything in NP, and all of NP reduces to it. It itself is an NP by verify and guess. Right? And here we're discussing that, you know, explicitly on the slide. So non-deterministically, to show that SAT is an NP, so I actually have a slide to answer that question, but I answered it anyway. But here's a slide to show that it's an NP. Non-deterministically guess each Boolean variable, and then at the end verify or, you know, make sure it works. And usually, you know, in fact, all of NP can be characterized by this method. This method is so general. All of NP can be characterized as a set of all problems for which guessing and verification is easy. That is polynomial time, for which you can verify solutions quickly. So if I give you a solution, can you verify quickly that that's the answer? And usually, it's pretty straightforward to see how. Just plug it in and see if it works, or verify that the statement is true, whatever the statement is. Okay. So that's kind of an alternative representation or description or characterization, I should say, of NP. NP is the class of problems that can be solved in non-deterministic polynomial time, or equivalently, it's a class of problems for which it's easy to verify that a given solution actually works for a given problem. And that's true in life in general, right? So for example, if I ask you, what's the square root of, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, that number, you know, that 9-digit number. It's hard to compute the square root of that. But if I give you a number and say, is that number x the square root of 1, 2, 3, 4, 5, 6, 7, 8, 9, that is easier to confirm that. How would you confirm that? Square it and see if it's equal to that other thing. So confirming that something is a square root of something is easier than finding it out to begin with. Okay. So NP-complete, the class NP, is the set of languages or problems for which verification is easy if you're given a solution candidate and asked, is that a solution or not a solution? Yep.
For the traveling salesman, how do you verify that a circuit is the minimum width?
So for traveling salesman, how do you verify that a given circuit is the minimum width? Because there's another parameter that comes in the input. The parameter is the maximum bound on the maximum bound on the tour length. So traveling salesman technically is not just here's a graph, give me a tour, but here's a graph and some integer k. Give me a tour less than k or less in length. So if I give you a tour, you can see the length of this tour and tell me if it's less than k. Now, here's a more subtle answer to this. Let's say you have a tour, and I didn't give you this parameter k. Okay. What you can do is do a binary search on the tour length, and for each one of those, ask if there's a tour of less than size k, and keep binary searching on this maximum tour length, and keep narrowing it down. So if you don't know what the tour length is, the optimal tour length, use the subroutine that asks you, is there a tour less than size k? And that you can do non-deterministically by guessing the tour and then verifying that it's less than k. And you can guess all tours, right? You know, start somewhere. Your first tour edge could be any one of your neighbors. So pick one of them non-deterministically. Your next tour edge is one of those neighbors of that node, so pick one of those. So you can guess the tour and then check its length. Its total sum length of edges. So determining whether a given tour, you know, is of a given length, you know, is a given length or less is easy. So if you don't know the tour length, you can say, okay, I don't know what the tour length is, but let's say I've asked if there's a tour of less than size 1,000. And if there is, I'll ask, is there a tour of less than size 500? And if there is, I'll ask, is there a tour of less than size 250? And so on. So I'm binary searching very quickly, and in logarithmic time, I'll converge finally on the answer. And that's usually how you can do that, by some binary search technique. So, but having said that, let's move on, because I worry that a lot of people are getting lost here. With the more, so I appreciate the deeper, more advanced questions, but I worry that 90% of the people are not following this, even the beginning of this. So I'm a little concerned at this point. So let's go back to basics here. So we mentioned Cook's theorem and Cook's paper. I think I showed this last time. This is all of Levin's paper in Russian, so no wonder it was so obscure. And we mentioned this encyclopedic treatment of NP-completeness. It's an old book, but it's an oldie but goodie. You should still refer to it. It's on the class website for extra credit. You can take a deeper dive into it. It's a very nice reference on this subject. It starts from scratch. It tells you all the definitions. And so does our own book. Zipser has NP-completeness in it, starting from scratch. And you should please all read that section of the book about NP-completeness. Otherwise, you'll just be staring at this with, it'll seem mysterious to you for a long time, or forever even. Okay, so let's talk about the robustness of P and NP. It's a very robust class, both of them, because compositions of polynomials yield more polynomials. Right? So the computation models are all polynomially simulated by all the other models. So if you want to simulate the supercomputer with an abacus, you can. You'll have to be a very large, darn abacus. But the point is, you can do this. Right? And certainly a supercomputer can simulate an abacus. And certainly a regular computer can simulate the game of life, Conway's game of life. How many have seen game of life simulations? Game of life is a universal computation model. But it can also be simulated with a C program on a Dell or by an iPhone and so on. Boolean circuits can certainly simulate orbital mechanics, or simulate pool games. But remember, pool was universal, so were orbital mechanics. So is DNA folding and chemistry of organic compounds. You can simulate that by a computer. And certainly it can simulate Turing machines. How can DNA molecules simulate Turing machines? Look in a mirror. You're a bunch of goo, and I'm not saying it in a derogatory way. I'm saying, in a proud, boastful way, that DNA computers can do all sorts of amazing things. We created the silicon contraptions. They didn't create us, right? So DNA can certainly simulate Boolean circuits, or any other. So the point is, all these models of computation here are all universal. They can all compute everything that's computable. But the point here is, they all can simulate each other efficiently in polynomial time. So the class P and NP is the same for a Dell computer or a supercomputer. It's the same class for an abacus. It's the same class for billiards. It's the same class for Boolean circuits, polynomial Diophantine equations like Hilbert's 10th problem solved by Matiasevich, DNA, and so on. They all can simulate each other with polynomial time. So it's the same class P and NP for all of them. So it's a very robust class. It's independent of the computation model. So whatever computers we'll have in 100 years, none of us will know. It's way beyond our lifetime. It's probably 20 generations of computers ahead. The same class P and NP will be true for them too. P and NP won't change in 100 years or 1,000 years, or even for an alien race, chances are. That's a pretty bold statement, but the point is, it's a very robust computation class. So any results we can derive about them is good for posterity and for lots of different situations. Yeah.
So is it possible then, by this universality, that we can look to nature for a solution to equals NP, or
Yes.
for evidence against it?
Yes. He's asking a very good question. And so can we look to nature to solve or resolve in the negative, this question of P is equal to NP? And people have tried that too. In fact, I looked at analog computations using physics or quantum mechanics or Newtonian mechanics, and they wanted to see if you set up a set of voltages or water pressures or angular momentum combinations of moving system, will now could you solve Satiafiability and traveling salesman-like problems in an analog way, using the universe to compute solutions quickly, where our digital algorithms cannot compute it on actual silicon computers. All these attempts failed. It's not to say that one day somebody may not find an end run in nature around P and NP. In fact, quantum computing, we hope, will inch us in that direction. Quantum computing might be one of those rare exceptions where it's not obvious that it can't do more than regular computers. In fact, the hope is that it can. That it can do arbitrary exponential kind of searches in polynomial time based on qubits, quantum bits, and superposition, and entanglement. How many even know what I'm referring to? Quantum computing? Okay, good, a few of you. If not, there's papers on the class website about quantum computing, so please read those for extra credit, fun, and profit. So quantum computing may be one of those. We don't know yet. That in itself is a pretty esoteric field, and we don't have working general quantum computers yet. There's primitive prototypes, and there's a couple of companies that sell them to you for $10 million each if you won't believe that they're selling you the real thing when they say we have a quantum computer for sale. But there's even debate about whether those are real quantum computers or just some fancy physics experiments, prototypes. Yeah.
So the P and NP clocks and quantum computers are the same as ours?
So for quantum computers, so she's asking, for quantum computers, is the class P and NP the same as our class for regular computers or circuits? We're not sure yet. They may not be, but chances are they will be the same. We don't know yet. We're hoping that using a quantum computer, you can solve everything in NP efficiently in polynomial time. But that's a really, really far-fetched.
But will that prove that P equals NP in our class?
No. So that will, even if you can show for a quantum computer that P and NP are the same thing, that they're so powerful, super powered, that they can solve everything in NP efficiently, that still will not resolve P is equal to NP for our normal computers, everyday computers, or for biological computers like we are. That still will remain open. But that's an excellent question. So people are looking into that because it's so important. And there's a Clay Institute, prize for, $1 million each, literally $1 million. And one of them is the P is equal to NP question. And there's 7 problems there in general. It's one of 7, and the number 5 has been solved already. And remember we said this guy didn't even want to collect his money for some strange reasons. Okay, a little bit about reduction types. So we said A is reduced to B using some polynomial time computation, mapping F. And we said that means A is reducible to B. That's denoted like this. But often we call that a many-one reduction because many things in A can reduce to B, but it's a one-shot. When you solve membership in B, you just solve it once with a single oracle call. But there's another type of reduction where you don't have to take one-shot kind of membership transformation and solve it with one hit. What you can do is use the subroutine in B many times. So you can solve a problem by multiple calls for the subroutine for the oracle in B and then solve A that way. And it's not known, that's another open question, is whether one reduction type with a single shot call to a subroutine is the same class of problems, NP, for this other subroutine, many calls to a subroutine type of transformation. So we don't even know if that's the case. So the class NP can vary based on whether you call it once or call it many times. But we define it as calling it once. It could be that by calling many times, you can solve a little more, when I say a little, some larger class than NP, slightly larger class than NP. That's possible. And nobody knows that either. But I'm just bringing to your attention that there's a couple of different reduction mechanisms, not just one shot, but many shots. They're also polynomial time. So historically, Richard Karp, in his famous paper that we're about to talk about, used this kind of many-to-one reduction, and Cook used this kind of one-shot kind of reduction. And here's the open problem I just mentioned, that we don't know if these two kind of reduction techniques yield the same class, NP, but they probably do. We just can't prove one way or the other. It's another open problem. By the way, most experts who've dedicated their life to resolving the P is equal to NP question believe that P is not equal to NP. So just so there's no so just so you don't think it's like a 50-50 even odds whether one is equal to the other, we don't know. 99.999% of people who know a lot about this stuff, who dedicate their lives to it, think that P is not equal to NP. And in fact, a lot of things in life depend on that fact. Crypto systems often depend that, heavily that P is not the same as NP. You know, we don't want your adversary to all of a sudden have an efficient algorithm to decrypt all your messages and secrets and emails and financial transactions. I mean, for example, Bitcoin could become completely irrelevant overnight if you can break the crypto system on which it is based. You know, and many other, you know, financial systems and transactional type, you know, databases where they depend on crypto for security. They essentially depend very essentially on the hope that P is not equal to NP. You know, in fact, that they base their lives and fortunes on this. We all do, in a sense. So just so you don't think it's like even odds, coin toss. You know, they're probably not the same. We just can't prove it, interestingly enough. All right, a few more things about satisfiability. So a restricted form of satisfiability called 3CNF, conjunctive normal form. So conjunctive means it's a product of sums. Product right here means and. Sum means or, of course, the usual. But here, every clause has at most 3 variables or variable negations. That's what we call a 3-sat. So 3-sat is every clause in the formula has at most 3 Boolean variables. No more and possibly less, but at most 3. But you can say exactly 3 if you'd like. The question is 3-sat NP-complete? Because we already know sat is NP-complete. That's Cook's theorem. So it turns out that you can easily show that 3-sat is NP-complete, even though it's a very restricted form of sat. And by the way, where does it stop? You know, why not say 1-sat? If I say 1-sat, sat is arbitrary Boolean formulas, but 1-sat is all the clauses that you're ending together have at most 1 variable or 1 negation of a variable. So how many say 1-sat can be solved efficiently? Good, now you're getting it. How can 1-sat be solved efficiently? What's an algorithm for a 1-sat?
Search linearly if you find a false, if it's false, if it's not.
Okay, but the variables are all ended together, right? And the variables are either plain variables like x or negation of variables like x naught, x prime. So if you search for all combinations of variables, you're back to exponential search. So you have to avoid doing an exponential search here. So what do you say? Yeah. So if x and x naught are ended together in the same large Boolean formula, it ain't going to happen. It's not going to be satisfied because you have an x and an x naught. So no matter what you assign for the x, it'll be false. The whole thing will be false no matter what the y's and the z's and the w's are. How many get that? All right. And it's an if and only if. So basically you have to look for an x and an x naught for every variable x, or a y and a y naught, or a z or a z naught. How fast can you do this, do you think, deterministically for n variables? Roughly, take a wild guess. N log n, or you know, if you're really careful, you probably reduce it to linear. But the point is, it's polynomial and it's a low-order polynomial. You know, certainly quadratic time will be plenty good to do it, even brute force. For every variable, go through the entire formula, look for the other negated version of that variable. If it's there, the whole thing is not satisfiable. If it's not there, go to the next variable, the next variable. How do we get this algorithm? So 1-sat can be solved in very quick deterministic time, polynomial time. Less than quadratic, certainly n log n, probably even linear. Okay, so 1-sat is not difficult to solve. How about 2-sat? Everything has a variable in its negation. That one is less easy to see how you'd solve 2-sat. But it turns out you can solve 2-sat in polynomial time also. It's just a little bit more involved. For extra credit, show me how to solve 2-sat in polynomial time. But 3-sat is NP-complete already. And here's a proof. So let's say you have a clause that has more than 3 variables. Like in this case, it has 6 variables. What you're going to do is create a bunch of 3-variable clauses from this longer clause that have all these extra variables, a, b, and c, and they're color-coded here. So you'd say x plus y plus a times a prime plus the next variable z plus b prime plus the next variable u plus the next variable v here, and finally string out all the other variables when you run out. So the claim is this, that this is satisfiable, this clause here, this big long clause is satisfiable, if and only if this whole formula down here is satisfiable, made of only 3 variable clauses. Why? This whole formula is satisfiable if x is true, or if y is true, or if z is true. That's what this formula says. Well, if x is true, this formula is true, this clause here is true, because x will be true, doesn't matter what y is. And then make a false, and this is still true because x is true. So x naught will be true because a is false. And it doesn't matter what z is. So make b true, right? And then b naught will, excuse me. So x is, if x is false, make a false. So a naught is true. So make b false, and b naught will be true. So it doesn't matter what u is. So make c false. So c prime is true, right? And it doesn't matter what these are. So if x is true, you can make this whole formula true. So this is satisfiable and this is satisfiable. If y is true, same thing. The point is you can set the a's and the b's and the c's to just what you need, such that if at least one of the variables is true, the entire formula down here will be true because of the way they're connected via these auxiliary variables, the colored variables A and B and C and so on. How many get this? So this formula is satisfiable if and only if that formula is satisfiable. So the point is you can take an arbitrary instance of SAT and convert it into an instance of 3-SAT that's satisfiable if and only if the original instance is satisfiable, which means if you have a fast algorithm for 3-SAT, this scheme will give you automatically a fast algorithm for arbitrary SAT, not just 3-SAT. How many get this proof? So we just proved that all of NP reduces to 3-SAT. How did we prove that all of NP reduces to 3-SAT? All we showed is that SAT reduces to 3-SAT. So why did we show that all of NP reduces to 3-SAT?
We proved that all of NP reduces to SAT.
Yeah, we proved that all of NP reduces to SAT. What was the name of that result? Say it, say it, say it. Cook's theorem, right? That was a big one. But now we know that all of SAT reduces to, all of NP reduces to SAT. And here we show that SAT reduces to 3-SAT. Now we know that all of NP reduces to 3-SAT, which makes 3-SAT what kind of a problem? NP, what's the next word? Hard, not quite complete. Why not complete? Because we have to show that it itself is an NP. Is that hard to do? No. I mean, do it like you did before. Guess and verify. And you'll know whether it's 3. So 3-SAT is definitely an NP. All of NP reduces to SAT because all of NP reduces to SAT by Cook's theorem, and SAT reduces to 3-SAT by this result here. So all of NP reduces to 3-SAT, which makes 3-SAT NP complete. So we've composed these two reductions. This theorem reduction with this reduction. By composing the reductions, we have one bigger reduction, end-to-end reduction. And is this end-to-end reduction polynomial time? How many say, yeah, it's polynomial time? Why? Not a hard question. You have two reductions, both of which are
Composition of polynomials.
composition of polynomials is a polynomial bingo. So Cook's reduction is polynomial time. This reduction is polynomial time. So you compose it to, and you get another polynomial time reduction. It could be a bigger polynomial than either one of the two. Right? If you have a polynomial that's quadratic and a polynomial that's cubic, compose it to it, you get a polynomial that's like 6th degree. Cubic squared or squared cubed, but that's 10 to the 6th. But it's still a polynomial, is the point. So you see how nicely polynomials compose to give you other polynomials. So their reductions compose to give you more polynomial time reductions, which means you can prove more and more problems are NP complete now and NP hard. Okay, this is what we said earlier about 1-SAT and 2-SAT. So is 1-SAT NP complete? Well, you can look at the variables and their negation, so quickly you can tell. Is 2-SAT NP complete? And it turns out you can solve that in polynomial time. For extra credit, do it. Here's a hint. Look for some implication graph and look for cycles in it. All right, so now we're going to go through a bunch of problems that are all NP complete, just so you see the scope of NP complete problems. The problem of cliques. I give you a graph and say, is there a clique of size 5 or 6 or 4? And a clique is a complete graph of all the nodes. So in a clique, every node is connected to every other node. They're tightly connected. So here's a clique of size 4. Here's a clique of size 6. Here's a clique of size 2. So the clique problem, I give you a graph and an integer k. I say, is there a clique of size k? K could be 3, 4, 5, 10, up to n, the number of nodes in the graph. How many understand this problem? Okay, seems easy, right? I mean, certainly there's a clique of size 4. You can see it. There's a clique of size 6. You can see that every node is connected to every other node. So why is that so hard? Well, it's hard because I don't always necessarily nicely paint the graph for you to show you where the cliques are. Right? Just like when I give you satisfiability, I don't tell you which one should be true, which one should be false using colors or whatever. You just get the plain formula. So the worst case, you can look at all subsets of nodes of size k, but that's a polynomial. That's not a polynomial algorithm in k, because k could be anywhere from 1 or to the size of the whole graph. Right? So here's a clique of size 5. Right? It's obvious because I painted it. There's a clique of size 3. It's amazing what you find on Google these days, besides questions to the exam answers. But if I give you this graph here, sorry, I couldn't resist. It's been bothering me, I have to say. If I give you this graph here, and I say, is there a clique of size 7? That's not easy to say. Right? I mean, there's a lot of nodes here, and which combination of 7 nodes will you take to determine the clique? Because now it's not nicely, painted so you can see the answer, right? So it turns out it's NP-complete. We haven't proved it here. We just mentioned that it's NP-complete, and here's another problem with NP-complete: set cover. I give you a universe of objects and a bunch of subsets, and I say, is there a combination of subsets, k of them? Because I give you the integer k, the number of subsets. Is there some combination of k subsets out of all these possible subsets that completely cover the entire universe of objects? So here, these are the subsets. This subset covers these 4, this subset covers these 4, this subset covers these 2. And I say, is there a combination of 3 subsets, say, that completely cover all these objects? And here there are. This subset here, and then this subset here. Now, if you take this subset and that subset, you might need 4 or 5, subsets. But the question is, can you do it with 3 for this example? And in general, that's NP-complete. We don't know if you can do it. So it's called the set cover. That's a cover set, not to be confused with set cover. But anyway, the set cover problem is NP-complete, turns out. And look how simple these problems are, right? But they're all as difficult as anything in NP. They're difficult as satisfiability, as traveling salesman, and any other problem in NP. Hamiltonian cycle. I give you a undirected graph, and I say, is there a way to traverse this graph in such a way that every node is visited exactly once? Now, if you do it with every edge visited exactly once, that's Euler tours. That one is easy to solve. You can do even Euler tours in linear time, but Hamiltonian tours, where every node is traversed exactly once, that's not easy to solve at all. So if I give you an arbitrary graph, is there a tour? That's related to the traveling salesman. Traveling salesman is a Hamiltonian tour through a graph. Not only that, it's got to be a tour of minimum width or minimum total, sum of edges. But even if it's unweighted, I just want a tour, any old tour. That's already NP-complete. Never mind if you put edges, you put edge weights on the edges and then ask for a shortest tour. That's even harder than that. Here, yeah. Because it turns out it's certainly it subsumes the one with no weights. So you can think about the one with no weights with weights of 1 on every edge. So it's a trivial weighted version. But it turns out both are in NP, and both are NP-complete. So they're just as hard as each other, even though one looks like a generalization of the other. Okay. Graph coloring. So we already mentioned that. I give you a graph and I say, is it possible to paint the nodes with, say, 3 colors to make sure that no 2 adjacent nodes in the graph that share an edge between them use the same color? There's like a coloring problem, you want to distinguish the nodes. There's entire books written on any one of those problems, by the way. I'm just showing you a couple of books on graph coloring. But these problems are so ubiquitous, so famous, so useful in practice that we try really hard to solve them for decades. For example, the graph coloring problem, compilers use them to assign registers in the machine code that they generate when they compile a language. So compilers use this as a subroutine. Of course, it can't be done efficiently. We don't know how, so they use a heuristic. I'll just give you an example where it's used in real life. So you've used this problem every day whenever you run code, whenever you compile a program. Okay, partition problem. I give you a bunch of objects with weights, and I say, is there a way to partition it into 2 subsets so that the sum of one subset is the same as the sum of the other subset? So just a bunch of integers. Is there a way to partition a bunch of integers into 2 subsets that have equal sums? As simple as this sounds, NP-complete. We don't know of any efficient algorithm to do this. Right? And we'll keep going next time with more NP-complete problems, and we'll actually begin to prove that some of these problems are NP-complete. We'll go do a few easy proofs first, and then proofs which are not so easy. So please, please read the book about NP-completeness, because things will just get more esoteric, not less. Okay? So we'll see you next time.
I have a solution for the Satiafiability of 2.
Oh, good. Good.
Okay. So each clause represents a graph from that variable, edge from that variable to that variable. Separate the graphs into the graphs that are connected separately. And then each one of those graphs you can solve by one of those clauses, and there's only 3 possibilities for that clause to be true, and that forces everything else to be either true or false.